You just might be right, Mr. Just might be right, Mr. Just might be right.
Good evening, ladies and gentlemen. It's Freemanjack on TNS Radio and Scottish Sovereigns on the land. I know the flash player's just crashed on TNS. Not that it really matters because I'm not listening to TNS at the moment. I'm broadcasting on it. Tonight's subject will be, as usual, of an adult nature and possibly containing adult language. So if you object to profanity, you may be better off not listening to me. I do tend to descend into the vernacular when the brain freezes. Tonight's topic, Goldilocks and the three universes. I'd like to try my very best to illustrate that there is significantly more than a coincidence about the fact that there is a universe at all and that there's anybody here to see what it is. Would like to put out a request. I've been working in three-dimensional spherical torsion physics. Little pursuit that I have, and would dearly like to experiment with some computer models, but am entirely lacking the PC skills, the techers, to bring that to any sort of fruition. So if anybody out there has got a bit of a dazzle at 3D computer modelling and thinks that they could possibly model the interaction of multiple rotating spheres on the screen for me, that would be fabulous. If not, I've got some slightly simpler stuff, I think, possibly simpler, to work with wave functions. Some of the considerations that I think have been left out of the double slit model bear some investigation, and obviously I don't happen to have a sort of an electron gun or a detector screen, as they're kind of laboratory equipment. But because of the predictable nature of waves, it would be very interesting to computer model a few variants on the double slit experiment that I can't seem to find anywhere in the literature, having been tried. Specifically speaking, a double slit experiment where instead of the two slits being parallel and vertical in the plate, which imparts a vertical polarisation to the wave, I would love to try it with two concentric circles as the double slits, and to possibly fiddle around with the sort of focal length away from the electron source. But anyway, that's just my my musings. If anyone's got any geeky friends that are into graphic manipulation, I'd love it if you could stick them onto me so that I could have a go at modelling some of these ideas that I'm working with currently. Excuse me, I need to cough. Yeah, so that's kind of what's been occupying my time of late. Excuse me. I need a swig of my tea. Oh, a noisy swig of my tea. Now, in the kind of researches that I've been doing over the last really more or less a year, targeted research that I've been doing for more or less a year, I've brought a number of subjects to the air which have been from individual disciplines, let's say the fields of biology or the fields of physics or the fields of sociology. And what a lot of these fields are pointing out is that we appear to exist in what I've cunningly titled the Goldilocks universe. What I mean by this is that we appear to be in the just right version of reality. Now, in the I'm going to have to refer to some of the terminology that anybody that knows me knows I absolutely despise, the likes of the Big Bang and black holes. But Big Bang theory and some of the physics surrounding black holes suggests that essentially we live in a balanced universe almost by chance, that there is no fundamental reason why the laws of physics that we experience in the universe as we know it should be in that particular way. There's no particular reason why the weak and strong gravitational electromagnetic forces rather should be the particular parameters that they are. And so falling out from Big Bang theory, we have this scenario that plays out whereby we, at the initial phase of the expanding universe at the very start of the Big Bang, we've got just a big ball of stuff brewing and boiling, and as that stuff expands, matter and antimatter are springing into and out of existence, springing into existence and then collapsing into each other because of their closeness and as their close proximity. And as the expanding universe fills its current form, there was a slight imbalance between the amount of matter and the amount of antimatter in that early universe. And had there not have been this slight imbalance, then essentially the reactions from that early phase of the universe would have simply have been a cancelling out exercise, and there would have been nothing created from it. So the stars and galaxies that we see are quite literally that. We are witness to that initial imbalance. Well, the issue that this brings up is that essentially, you know what I mean, the you could easily have ended up with the baby bear universe, the universe that was too cold, that had too much stuff in it, not enough energy. And if this balance of decaying subatomic particles and interacting subatomic particles had gone slightly differently, then we could have easily have ended up with a universe with so much hard stuff in it, stars and planets and stuff, that the gravitational forces would have overwhelmed the repulsive forces within the early universe, and the universe would have simply collapsed back down into its initial phase, probably then to re-emerge. Or we could have the kind of daddy bear universe, which is far too hot, and in the daddy bear universe there's so little matter and so much energy that the repulsive forces overwhelm the gravitational forces in that universe, and you end up with a complete runaway universe, something that would create almost no stars or galaxies, because the expansion would be too great and would overwhelm the collapsing gravitational forces that kind of condense stuff out of the ether. So, as we can see, we're in this kind of, we're in this mummy bear universe, which is just right, that all of the various strong and weak forces all pretty much cancel each other out, that atomic structures are largely mirrored on a broad scale, and as a result we have the universe as we perceive it. Well, no, like I say, the cosmologists will have you believe that the reason for that chance coincidence that we should end up with this universe that is so essentially perfect for our existence is simply that because had the universe have not been so perfect, that we wouldn't be here to observe it. And I can kind of see the logic behind that. I mean, obviously in a universe that emerges and collapses routinely on itself, there's not going to be an awful lot of chance for persistence of life or intelligence in a universe like that. And in the one that flies apart at such an alarming rate that stuff doesn't really coalesce, pretty much the same thing holds. So the reason why there is biology and intellect in such a universe as our own is simply because the laws of that universe, the physics of that universe, don't disallow it. So, on the larger scale, we are in this position where we are in a universe that is fit for our inhabitants. But then we add to that the fact that we make all of these reasoned arguments about what the universe was and what it's likely to become, and observations like the Hubble constant, which measures the expansion of the universe, which Hubble was convinced would actually be 1, or is near to 1, has made no difference. But a 1-to-1 ratio, in other words, pretty much not expanding, is actually found out, or theoretically, not only is it expanding, but it's accelerating, which really was an unexpected finding. Where was I going with Hubble? Yes, and so we live in this expanding, accelerating universe. Well, only a very short time in the past, the theoretical Big Bang universe would have provided us with such a hot, dense place that light couldn't have been emitted by it. And then we have the point at which the expansivity of the universe becomes so great that light can no longer reach us from the furthest reaches of the galaxy, so we would have no way of making an efficient measurement. Well, again, we're in this just so situation where we give the universe an approximate age of 14 billion years, and yet the observable universe, according to the physics of expanding universe theory, would be approximately 13.5 billion years across. In other words, we happen to exist at the time in the expansion of the universe where it is possible to calculate the theoretical size of the universe. At any time before this, there would have been too short a run of initial time and not enough data to project potential time. Any later, there wouldn't have been the distant stars in order to be able to measure the furthest points of the galaxy. So we're given this, the universe. So we're given this thing called the observable universe, which correlates almost perfectly with the known universe. And again, I suggest to you that that's rather coincidental, that the possibilities of all of these various coincidences have to be considered in kind of in compound, if you're a bookie adding up odds, say on the accumulator on a pony race, you would add up those odds with the compound effect of each race, making the winning of the full set of races compound the potential winnings. So, because that's how the risk is calculated. And this is sort of the same way that I'm looking at this subject, that we're confronted with so many different layers of coincidence that it seems against the odds that this should simply be, as the cosmologists would have you believe, that it's just that we happen to be in a universe, in a version of the universe that is observable at a time that it's observable. Anyway, I'm going to go on in a bit to talk about the biosphere and our local part of the universe, and exactly how exquisitely balanced and how exquisitely perfect it is for life on such a broad scale that, again, coincidence would be hard to use as a reasonable explanation as to why that should have come about. Right, and so the miracle, it's hard to find words that don't really kind of drift into the realms of spirituality when we're describing the earth, but the the miracle that is the biosphere, the biology on this planet, again, is reliant on so many different physical properties of the universe that we find ourselves in. Not least of these is the atomic properties of water. First of all, it's something that we don't really consider very often, but water is a very strange substance. The anomalous behaviour of water is the list is huge. But the primary thing to think about here is essentially that there is no dry air as such on this planet. Every piece of air, every volume of air has water vapour in it. So essentially the thing that we walk around in thinking of as air would in fact be more accurately described as water vapour. We live on this planet where water is so very keenly balanced to the temperature zones of the Earth that we have a planet where all three forms of water, all three primary forms of water, exist simultaneously. We have the ice at the poles, the water of the seas, and the water vapour of the air that we breathe. And this has had an incredibly key influence over the way that biology would have had to have evolved out of organic chemistry or inorganic chemistry. And key to this function, key primarily to this function, is the anomalous expansion of water. Virtually every material known to man contracts, shrinks as it gets colder. One of the very few exceptions to this is the water molecule, or water. And water, when it freezes, as it gets close to freezing, actually gets to 4 degrees above zero, and then begins to expand again, and it actually expands by nearly 10% over the gradient between 4 degrees and 0 degrees. This is quite a shallow gradient, and it's essentially this action, this expansion of anomalous expansion of water, that has created the mineral salts that were required to initiate biology on this planet. So essentially water finding its way into cracks in igneous rocks and breaking apart those rocks, creating the first sands and generating the materials for the very first ever sedimentary rocks. Other than that, we would be sitting on a planet lapping with toxically salty water and just big slabs of kind of granite poking up out of the water. Or if not granite, then certainly igneous rock. So we've got this kind of interconnectedness between water and the shaping of the land, and again, this is facilitated by this ready change of state that water is in this kind of medium state at the temperature that this planet runs at. And so we find water easily being evaporated off of the surfaces of the ocean and forming cloud structures and being deposited on the surface of the land, and thereby washing the surface of the land out into the sea. Well, it's entirely possible that these first mineral nutrients, these first liquefied nutrients, would have been those which gathered in various rock pools, and that those would have been the places where under the furnace of the powerful ultraviolet rays and gamma rays from the sun could possibly have imparted enough energy to naturally occurring chemicals to essentially lead to how to describe it really, to the coalescing of the initial RNA molecules that would have been required for biology to have started. The RNA question is very touchy subject. RNA and DNA are very much like the chicken and the egg, because there's no known natural source of RNA, which is the building block of DNA, without the action of biology, which kind of leaves us in the situation of having to explain how a molecule like DNA could possibly have sprung out of a world where RNA wasn't already present. And yet without the biology of DNA, we can't explain the presence of so much RNA. But we have to assume, to some degree, that some physical condition on the primordial Earth allowed for these kind of hot, soupy pools of chemistry to have led by accidental combining of compounds in varying concentrations, and those compounds being complex enough to be able to self-assemble. And this is really, this is a key problem. Self-assembly is a real kind of key problem to the whole history of biology. The initial phases of self-assembly, we can easily model and explain the mechanisms of self-assembly once we have biology. But without the biology, it's very hard to explain the initial self-assembly. There's a lot of research going on into lipids and their nature due to surface tension to form sort of natural spheres, and it's entirely possible that would have been the action, the collating of chemicals within a sealed body of the sphere of the lipids. Would have been an action similar to sea foam, where in fact that's an algal product, but an action of a churning sea that would have produced these lipid-like substances that could possibly have captured the first pre-RNA molecules. So we've got water being key to the reducing of minerals from their pre-existing hard state of quartzes and the likes, down to the more how can I put it? More preferential to life that some of the sedimentary rocks and sediments and mud would have accommodated. We've then got, once biology has emerged, then suddenly, in addition to clouds of water vapour and stuff floating around the planet, now we suddenly have the first self-regulating biological systems. The initial ones were, I believe, they were stromatolites. These are essentially barely organic kind of algae-like clumps that essentially take up the dissolved salts in the water, and through initially through chemosynthesis, and then to some degree, I don't know that stromatolites do actually rely on photosynthesis, but I would have to look that up. They're basically like a red algae, and these red algae fix the minerals and essentially grow stone. It's known as beach stones. They grow like sort of little pebbles on the beach. And the thing about these stromatolites is that they would have been the first organisms capable of producing oxygen. And so as soon as we start to see oxygen being produced, the boundary between before the presence of high levels of oxygen in the atmosphere and after it in the geological record, the planet rusted. We're sat on a ball of iron with what would have been quite a lot of iron on the surface in its unoxidised state in an almost inert sort of nitrogen and carbon dioxide atmosphere, and suddenly we introduce a load of oxidising agent to it. So in this initial kind of biological phase, the first thing that you would notice was that the sea would have turned blood red, and so would most of the land as well. So a very Mars-like appearance we must have taken on at the time. anyway, when some of this oxygen was reacted out, we start to see biology recycling it and creating what we now know to be the kind of biological carbon dioxide cycles and oxygen cycles of biology. You know what I mean? Algae and plants breathing out oxygen and taking on board carbon dioxide to produce their kind of plant matter. First thing that does need correcting slightly is this in people's thinking, is this belief that seems to have sprung up that somehow the rainforests are the lungs of the planet. This is just an utter nonsense. Essentially the net carbon footprint, to use the jargon, of a forest is zero. It doesn't sequester any carbon dioxide, and it doesn't emit any carbon dioxide. The reason for this is that plants like us are creatures that respire. That means that they breathe in and breathe out. They only do this once a day. They breathe out during the day and breathe in at night. And essentially, apart from the small amount of carbon dioxide that's actually sequestered to make the cellulose of the plant fibres, the amount of carbon that's removed from the atmosphere by any land-based plants is absolutely nominal, and that all of that is simply in the plant material that gets bound up in anaerobic swamps and things like that, where the hydrocarbons can't be re-released to the atmosphere. So the actual oxygen that we breathe has nothing at all to do with land-based plants at all. That's actually given to us, and thank God it is, by the blue-green algae in the ocean. There's a layer of blue-green algae that lives at about 1 metre depth over the entire, or most of, the Earth's oceans. And these little blue-green algae photosynthesize sunlight, and they react dissolved carbon dioxide in the water with sunlight to create the sugars that they rely on for their biology. As a result, they've got a spare oxygen molecule for their carbons that they were looking for. Well, this oxygen molecule is released as little gaseous bubbles. Well, of course, these little critters live in 1 metre below the surface. That little bubble is going to come. I don't know if you've ever tried to hold a football down in the swimming pool, but if you have, you'll kind of know how buoyant a bubble of gas is in liquid. So obviously these bubbles rise up to the surface and are released as gaseous oxygen. And once they're released into the atmosphere, apart from the small amount of oxygen that's then reabsorbed into the surface of the water by compound mixtures, that oxygen is available for us to use. These little blue-green algae as well, they're pretty impressive little fellas, because we look at the White Cliffs of Dover and think that it's made of rock, but in fact it's made of skeletons. It's made of the skeletons of these little sea creatures. And that whole stack, I mean, you could probably hold several tens of thousands of these creatures in a few square millimetres of chalk. And so to consider the amount and time scale that we're talking about to deposit the layer of bodies that was required to produce something like the White Cliffs of Dover, it's just phenomenal to consider. And essentially these were the organisms, these were the carbon dioxide scrubbers, these were the little chaps that were responsible for reducing the levels of carbon dioxide on the planet from inhospitable to biology to being hospitable to biology as we find them today. And the way that it did that was by absorbing that suspended carbon dioxide in the water column, using it to create its internal structures, its skeleton, and then when it died, this skeleton drops out of the water column and basically falls to the sea floor and sequesters that carbon in the form of chalk, in the form of calcium carbonate at the sea floor, where it's never going to return, or never in any conceivable future going to return to being gasified carbon dioxide again. So this is a permanent reserve of carbon sequestering biology that is primarily the functioning part of the biosphere. That essentially the oxygen that's released by these little critters and the sequestering of the carbon dioxide of these little critters is entirely self-regulatory, because the oxygen that they release is a key part of the evaporative processes on the surface of the seas. So to some degree these critters go to creating clouds, but also in a kind of beautifully cyclic link. The amount of carbon dioxide in the air regulates the amount of carbonic acid in the rainwater. Carbonic acid will dissolve limestone. So when acid rain falls on mountains or whatever, depending on how much carbon dioxide there happens to have been in the atmosphere where that water vapour was drawn up off the surface of the oceans, depends on how acid it is. Well, when that rain then rains on mountains, it dissolves the limestone, which is then washed out through the river systems out into the open waters, and guess what? It's a plant food for these little fellas that sequester carbon dioxide in their skeletons and take it to the bottom of the sea with them at their death. So essentially we have this perfect biofeedback loop whereby these blue-green algae are more or less regulating the climate of the planet. Now that may seem to be quite a coincidence, but then we go one step further than that and we go to the next level of biology, the insects, and we come to the farting termite situation. Now, as far as land-based plants, the termites are reckoned to consume, it's in the high 90s% of all of the hydrocarbons produced by all of the plants over the course of any given year. I found that figure to be quite startlingly high, but when you consider the proliferance, how prolific these creatures are, and how effective they are at harvesting, and considering as well that they don't necessarily harvest foodstuffs that are being utilised by other creatures, so the fresh green stuff isn't necessarily what they're after. But essentially these little fellas digest all of these hydrocarbons, and this produces a fairly significant amount of methane from the digestion processes in their gut. Well, most of us would be quite content with releasing that methane at our leisure. But not these little fellas, not termites, oh no. They've got a row of 6 little sacs down each side of the inside of their abdomen. And these little sacs slowly fill up with methane during the course of the day. And then, once it's gone dusk, the termites then let one fly. They release these little the valves on these little methane sacs, and the methane is allowed to escape. Well, the consequence of this delightful little adaptation is that when that methane is released at night, it rises up into the upper atmosphere, and it interacts with ozone up there. It interacts with oxygen up there to create ozone. Now, if that same methane had been released during the daytime, methane is actually an ozone depletant. This is why it's such bad news that cows produce so much of it. The very same methane that goes up into the upper atmosphere and chemically produces the ozone, the mirror layer of atmosphere that we've got that protects us so much from the sun, that it depletes ozone, that the action of methane and sunlight it knocks apart the ozone molecules. So we have termite farts regulating the amount of ozone that we have. Well, what's significant about that? Well, the significance about that is that because termites eat by far the largest majority of all of the hydrocarbons, all of the plant material produced during the course of a year, and that the volume of that plant material is regulated largely by the amount of solar radiation reaching the planet's surface, that essentially, by releasing their methane only at night, termites regulate not only the temperature of the planet, but the amount of biology on it. That if the plants were to start running out, then the termites would start to run out, and we would see less methane being released at night. We'd see lower ozone levels, we'd see higher solar radiation levels. We'd get a bit of a greenhouse effect going on there, but the plant life would love it. And so we've got, I mean, the action of tiny blue-green algae and the action of tiny termites controlling, being the governors, being the regulatory mechanisms that have basically allowed the temperate Earth to remain temperate. I mean, some estimations have said that that we should essentially be another Mars-like planet, that we shouldn't have any atmosphere, that the increase in solar radiation over the course of biology during the lifespan of this planet, we should now no longer have a biosphere, that it should essentially have been evaporated away, irradiated off. But because of these self-regulatory measures, that each time the solar radiation has increased, so has the self-regulation, and kept it in check. And so here we are on this just so Earth. And again, I suppose the argument could be held that the reason why the Earth is so just so is that in order for biology to emerge by so many seeming coincidences, possibly means that this is a unique place in the universe, that this has only happened the once, and that what we're viewing from inside of our little unique part of the universe is missing a huge swathe of our uniqueness from our own kind of world view. So again, this is possibly, it's one of the reasons why I have so many problems with the concept of kind of alien life, is that yes, it is possible, but if it is there, it's likely to be so unlike anything that represents life that we know, that we wouldn't even know it if we saw it. Certainly, I think it was James Crick, one of the discoverers of the DNA molecule. No, hold on, James Watson. Oh, well, anyway, one of them went on to do spectral analysis of interstellar dust, and discovered that interstellar dust gives the same spectral analysis lines as biology does. The spectral spectral graph from interstellar space, when you're not pointing the spectral analyzer at a star, comes back as more or less identical to biology, biological organic compounds. So we may well be living in some kind of a panspermia world where life is everywhere, but I certainly think that advanced life, such as what we experience on this planet, is incredibly unlikely elsewhere. Okay, so we've got this just so universe and just so planet. Let's look into a few other sort of observable effects that we can take into consideration. Last week I didn't come to the mic due to teenager problems. I had actually intended to come to the mic and say a lot more. I did come to the mic, but just wasn't able to cover the subject as well as I'd hoped. But last week I covered the matter of the exponential function when considering natural and man-made systems. The primary pod was a mathematician describing how the implication of the exponential demand on petrochemicals and fossil fuels was essentially leading us to a financial cliff I think he wouldn't mind it being described as a term that's in the press rather a lot lately. Well, what I'd like to do is also illustrate the other side of the exponential function, and that's the exponential function that appears to be applying to the evolutionary development of the human mind, of human activities. And here we see a classical kind of ski slope graph, and I've actually been watching these various ski slope graphs and their predictions, and the consequence of this is that if you're modelling something through a graph where you have a baseline of time and a kind of Y scale of human development, capacity for storage, speed of electronics, amount of interconnectedness between various people through social media networking and stuff, then we appear to have this sort of clear exponential that the ski slope is so steep where we are that it's all but vertical. Now, it's nonsensical to assume that we can have a vertical graph of evolution over time, because that would simply mean that we would continue evolving at an ever faster and faster rate, and time no longer existing, that time would have had to have come to a standstill, which obviously isn't possible, and yet the trends all appear to point to this. Well, they all appear to point to this unless you use a logarithmic scale for your timeline. By this I mean that instead of having a linear scale where each division is a minute or an hour or a week or a year or a decade, that each division is a factor of the division before, whether that be a 5 fraction, so the first digit would be 1 and the second digit would be 1.618 or whatever. You then take that ski slope curve and you see that ski slope curve stretched out into a straight line, into a corrected trajectory. And it strikes me that this makes some very serious, in which case there is no point on that particular graph where growth becomes a vertical component, that essentially we see an ever-growing graph, but at no point do we reach the impossible stage of time needing to come to a standstill in order to be able to achieve any more development. So we've got some fairly extraordinary questions to ask ourselves about the nature of time and the implications of that possible logarithmic, non-linear nature to the play of time, that if we roll that back into the past may well explain an awful lot of the kind of archaeological and geological anomalies that we see, and would certainly raise some very serious questions about our calculations about the universe that we live in. Time and the distortion on time by mass is something that really doesn't seem to be factored in to a lot of these equations. Many of most of the physics that I have been researching essentially deals with time as if it's constantly in current regular time, and that the physics that apply to this time are the physics that apply to all of time, and that is very likely to be a grand generalisation. It may well be that the change in the periodicity of time is so gradual, and that from within time you would not be able to detect the change in front of you or behind you, simply because you're in your kind of like little private bubble of time. So there's that to consider. Now, this doesn't detract from the fact that this still implies an exponential function, Well, with an exponential function, the second pod that I played last week was Buckminster Fuller, describing how his life from 1893, I think he was born in, had played out as a child, from throwing paper planes around as a child and being told quite sternly by his parents that manned flight wasn't possible because you couldn't fly. It wasn't possible for a man to fly, and how the Wright brothers, when they'd first announced their historic flight, had been broadly dismissed, and that sceptical engineers set about trying to prove how the fraud had been committed of this so-called flight. He then goes on to explain how, in the history of the telephone exchange in America, that due to the advances in the engineering capacity to carry more data down smaller and smaller pipelines, actually led at one point to the telephone companies being a net seller of copper, because their old system had been so reliant on such vast quantities of copper, and because of the advancements in technology, had allowed them essentially to pare back their system and do more with less. And this is essentially what we now find ourselves presented with, is the ability to do more, not only more with less, but more with time with less. So not only are we able to do more with less now, but in the next 10 years we'll probably, if the exponential function holds, that we will be able to do not only more than we've done now, but more than we've done now and ever in the history of mankind, just in the next 10 years. And that's a fascinating prospect for me. That's a truly astounding prospect, and to some degree, with certain measures, if you want to project that backwards through history, you can see that graph is held up, that we appear to be on that trajectory. And so, I'd like everybody to consider the requirements that this places on us as a society, that where our grasp of the new, of the novel, would have come in a reasonable trickle, a manageable rate at times in the past, we're now going to be inundated with a deluge, possibly a deluge beyond our actual capacity. But that doesn't necessarily mean that we have to reject it out of hand, and in fact it will be burdened upon us as those who don't have the capacity to be able to cope with that amount of deluge of data, that we need to raise our youth to be capable of managing that kind of a data flow in order to be able to make use of the exponential that we're presented with. And so I think computer sciences and the teaching of logic, I think, is probably key for the future generation. I met a lovely Bristol University lecturer who used to talk about digital natives, digital immigrants, and analogues. And he said that our generation were the digital immigrants, that we could speak digital but we spoke it with a slight accent, and our children are the digital natives. They've been born and raised into a digital world, and our parents' generation are the analogue generation, that they have absolutely no concept of what new technology is either capable of or how to make use of that capacity. So just to expand on the lipids, I noticed somebody in the chat box mentioned any liquid with a surface tension naturally forming spheres. I noticed they've disappeared from the chat, so I assume they're not listening anymore. But just in reference to their question there, lipids are a very unusual case. They have a polarised molecule, where one end of the molecule is very hygroscopic and one end is very hydrophobic, and as a result they've got this, that's why we use them as soaps, is because essentially they have the capacity to bind with other molecules, but in a polarised way, so they form spheres around other substances, basically locking those spheres away. So in the process of laundry, it's locking away the dirty water so that it can't re-affect the clothing, and it's then taken away in a suspended lipid in the wash water. Okay, so where did I want to go with that? So it's the kind of the onus is on us to keep up to some degree, and that perhaps many of us kind of left school and thinking that was the end of our kind of educational career, or perhaps left university. And I would suggest that the onus is on us now not to relinquish that hunger for understanding, because if we're going to impart any sort of level of sensible interpretation of the world that they find themselves into the youth, then we need to find some way of imparting those kind of considerations. I don't know if I'm going to go into the three-dimensional force vectoring. I need to be clearer on this myself. I've got a bee in my bonnet about tetrahedrons at the moment, and moreover tetrahedrons made up by sort of ping-pong balls. It's funny that Dr. Rock announced he'll be covering, I think he described it as the holographic paradigm next week, because that was one place that I was going to go this week, but I won't bore you with holographic universe theory if Nick's going to cover it next week, especially with the slideshow. Wow, you lucky people. The holographic universe theory is definitely tying in very keenly to my inquiries into tetrahedrons and kind of atomic ordering and the shapes of crystals and the kind of whys and wherefores. I might say, if anybody's up for doing some three-dimensional force vector modelling in some sort of computer program, I would love to work with you, try and get some means of visualising some of the concepts that I'm trying to wrap my head around. And a small example is that with 4 ping-pong balls gathered together in the smallest of confines, that if you were to rotate one ping-pong ball where it impinges on the other 3, that it would impart spin and angular momentum differently to all 3 of its partners. And I'm trying desperately hard to visualise the interactions between those spinning ping-pong balls. And worse still, at the moment, that's still in kind of regular 3-dimensional space. It's entirely possible that I'm going to have to model the effect of anti-ping-pong balls in some kind of a hyperdimension in order to be able to to actually get to the finished product, finished theory. Yeah, this kind of tetrahedral thing is just in case anybody isn't aware of what tetrahedron is. Tetrahedron is a 3-sided pyramid or a 4-sided object. It's the basic unit of geometry. It's the smallest geometrical unit that can describe 3-dimensional space, and I've got a distinct suspicion that the kind of considering of spatial dimensions as being largely cubic, that when we envisage 3-dimensional space, we largely envisage it as a cube. I would actually suggest that it's more likely to be tetrahedral. And just one little thing to come out. I mean, Buckminster Fuller researches that Buckminster Fuller would tell all his students to reject the terms up and down that he suggested that the terms up and down were more accurately described as in and out, because our concept of up is related to our centre of gravity of the planet, and so of course up to somebody in Britain would be 180 degrees out to up to somebody in, say, New Zealand. So he would actually get his students to stop using terms like upstairs and downstairs and replace them with outstairs and instairs, just as a way of kind of remodelling the way that you actually think about the reality that you exist in. I mean, Tom Campbell talks about the kind of flat world model being a suitable model if you're building things on a small scale, and it's only when you get up to things the size of the Parthenon that the diverging parallel lines actually become an issue. They're up isn't the correct term, and out should be considered. Yeah, essentially all of this discussion of how the physical universe evolved is really moot in the face of holographic universe theory and Tom Campbell's digital virtual reality theory, in as much as in holographic universe theory it would appear that the stuff and substance of the universe is a holographic projection from some distant two-dimensional object. Personally, I struggle with that one. In Tom Campbell's digital virtual reality theory, the perceived universe is essentially a one-dimensional a data stream, and that what we perceive of reality is merely our decoding of that data stream, in much the same way that a virtual reality is created in a simulations game. If either of these are correct, then what we would have to see is a coordinates system within the encoded data. And this is one of the reasons why I'm pursuing this tetrahedral kind of vector rotation thinking, is that if you were to model a holographic reality in which all of the values of every region of that holographic reality were encoded into every last finite detail, as it would appear our holographic reality is, then that would require a set of coordinates for any given quanta of volume. You would have to have a set of known parameters, a set of key parameters to describe that volume. And my thinking on this is that the tetrahedron is the most likely surface on which that hologram would need to be projected or reconstructed. And that the nature of reality that we see itself is the kind of concertinaing of a kind of tetrahedral grid, which from various angles would appear very much like the flower of life drawings that you see in the likes of sacred geometry. And certainly, I mean, one of the things that really kind of set me up like a rat up a drain pipe with this particular subject was I was tripping my bollocks off on a load of mushrooms a couple of years back, and I was sitting here looking around the room listening to music, and I noticed that the room was kind of started scintillating with these kind of little bright points of light, and I'm sitting there musing on this sort of scintillation while rolling a joint on my lap, and I have the compound influences of both being very, very blind and very, very vain. And so, although I need glasses in order to be able to see anything clearly, I also very rarely wear them. As a consequence, the only time that I would wear my glasses during the skilling up process would be while I was putting the weed in the joint. So I've got to that part of the process and lifted my glasses to my eyes to be able to see what I was doing on my lap. And suddenly these, what appeared to be fairly random scintillations, suddenly came into crisp focus, and it was a sort of flower of life like lattice that appeared to be draped over all of the solid objects in the room, and that the scintillations that I'd been seeing were like little ripples running down each of the curves of the circles of the flower of life, and creating little kind of shiny spot where they met at the intersections. And I would have probably have passed this off as a hallucinatory experience, and purely a hallucinatory experience. However, I don't really necessarily hold that there is such a thing as hallucination. I've certainly never specifically seen anything that wasn't there by way of hallucination. There's always just simply been a change of the nature of the substance that you're looking at. And in this case, moreover, the fact that it was brought into crisp focus by my spectacles would appear to point to it being an external event. And I find it very hard to conceive of a way that an optical device could influence the nature of a hallucination, if that's what it was. If it wasn't hallucination, then one would have to suggest that in the defiltering process of the hallucinogen, removing the filters that prevented me from seeing the nature of the substance that was already pre-existing. So that kind of set me thinking in kind of 3 dimensions on the sort of flower of life thing. And recently I've been realising that this is essentially would be the perfect way of encoding the structure and the fabric of reality as we perceive it, because this would allow for coordinate and coordinate points in 3-dimensional space, and sort of relativistic motions between those coordinate points, which to my mind may well describe the nature of the stuff around us. Anyway, that's my musings on it. This has been absolutely twisting my head. I'm up bloody day and night thinking about this shit at the moment, so I think that's probably about all you're going to get from me about this tonight. I'm still really kind of in mid-problem. I know we're supposed to be seeking solutions here, but I'm too busy looking at problems. But I do have lined up a rather interesting mainstream media description of fractal geometries, which hopefully will be able to explain fractals to anybody that doesn't really grasp them. And the reason why I'd like to play this is simply because even if you think you understand fractals, that this particular program has very nicely illustrated the way in which the world around us can be recreated through the use of fractals. And for me, this is a key pointer to the mechanism through which a holographic reality may be observable. Anyway, this was from PBS Nova, and it's called Fractals Hunting the Hidden Dimension.
In 1978, at Boeing Aircraft in Seattle, engineers were designing experimental aircraft.
Exotic things with 2 wings or 2 tails or 2 fuselages and just weird stuff. Because who knows, it might work.
A young computer scientist named Loren Carpenter was helping them visualize what the planes might look like in flight.
I would get the data from them and make pictures from various angles, but I wanted to be able to put a mountain behind it because every Boeing publicity photo in existence has a mountain behind it. But there was no way to do mountains. Mountains had millions and millions of little triangles and or polygons or whatever you want to call it, and we had enough trouble with 100, especially in those days when our machines were slower than the ones you have in your watch.
Carpenter didn't want to make just any mountains. He wanted to create a landscape the planes could fly through. But there was no way to do that with existing animation techniques. From the time movies began, animators had to draw each frame by hand, thousands of them to make even a short cartoon.
That's why they call me Thumper.
But that was before Loren Carpenter stumbled across the work of a little-known mathematician named Benoit Mandelbrot.
In 1978, I ran into this book in a bookstore, Fractals, Form, Chance, and Dimension by Benoit Mandelbrot, and it has to do with the fractal geometry of nature. So I bought the book and took it home and read it, cover to cover, every last little word, including footnotes and references, twice.
In his book, Mandelbrot said that many forms in nature can be described mathematically as fractals, a word he invented to define shapes that look jagged and broken. He said that you can create a fractal by taking a smooth-looking shape and breaking it into pieces over and over again. Carpenter decided he'd try doing that on his computer.
Within 3 days, I was producing pictures of mountains on my computer at work. The method is dead simple. You start with a landscape made out of very rough triangles, big ones. And then for each triangle, break it into 4 triangles. And then do that again, then again and again and again and again.
Endless repetition. What mathematicians call iteration. It's one of the keys to fractal geometry.
The pictures were stunning. They were just totally stunning. No one has ever seen anything like this. And I just opened a whole new door to the new world of making pictures. And it got the computer graphics community excited about fractals because suddenly they were easy to do. And so people started doing them all over the place.
Carpenter soon left Boeing to join Lucasfilm, where instead of making mountains, he created a whole new planet for Star Trek II: The Wrath of Khan. It was the first ever completely computer-generated sequence in a feature film.
Fascinating.
Made possible by the new mathematics of fractal geometry. Benoit Mandelbrot, whose work had inspired that innovation, was someone who prided himself on standing outside the mainstream.
I can see things that nobody else suspects until I point out to them. Oh, of course, but they haven't seen it before.
You can see it in the clouds, in the mountains, even inside the human body.
The key to fractal geometry, and the thing that evaded anyone until really Mandelbrot sort of said this is the way to look at things, is that if you look on the surface, you see complexity, and it looks very non-mathematical. What Mandelbrot said was that think not of what you see, but what it took to produce what you see.
It takes endless repetition, and that gives rise to one of the defining characteristics of a fractal, what mathematicians call self-similarity.
The main idea is always, as you zoom in and zoom out, the objects look the same.
If you look at something at this scale, and then you pick a small piece of it and you zoom in, it looks very much the same.
The whole of the fractal looks just like a part, which looks just like the next smaller part. The similarity of the pattern just keeps on going. One of the most familiar examples of self-similarity is a tree.
If we look at each of the nodes, the branching nodes of this tree, what you'll actually see is that the pattern of branching is very similar throughout the tree. As we go from the base of the tree to higher up you'll see we'll have mother branches, then branching then into daughter branches. If we take this one branch and node and then go up to a higher branch or node, what we'll actually find is, again, that the pattern of branching is similar. Again, this pattern of branching is repeated throughout the tree all the way, ultimately, out to the tips where the leaves are.
You see self-similarity in everything, from a stalk of broccoli to the surface of the moon, to the arteries that transport blood through our bodies. But Mandelbrot's fascination with these irregular-looking shapes put him squarely at odds with centuries of mathematical tradition.
In the whole of science, the whole of mathematics, smoothness was everything. What I did was to open up roughness for investigation.
We use mathematics to build the pyramids, to construct the Parthenon. We use mathematics to study the regular motion of the planets and so forth. We became used to the fact that certain patterns were amenable to mathematics. The architectural ones, but largely the patterns of human-made structures where we had straight lines and circles and the perfect geometric shapes. The basic assumption that underlies classical mathematics is that everything is extremely regular. I mean, you reduce everything to straight lines,
circles, triangles,
flat surfaces,
pyramids, tetrahedron, icosahedron, dodecahedron,
smooth edges.
Classical mathematics is really only well suited to study the world that we've created, the things we've built using that classical mathematics. The patterns in nature, the things that were already there before we came onto the planet, the trees, the plants, the clouds, the weather systems, those were outside of mathematics.
Until the 1970s, when Benoit Mandelbrot introduced his new geometry.
Mandelbrot came along and said, hey guys, all you need to do is look at these patterns of nature in the right way, and you can apply mathematics. There is an order beneath the seeming chaos. You can write down formulas that describe clouds and flowers and plants. It's just that they're different kinds of formulas, and they give you a different kind of geometry.
The big question is, why did it take till the 1970s before somebody wrote a book called The Fractal Geometry of Nature? If they're all around us, why didn't we see them before? The answer seems to be, well, people were seeing them before. People clearly recognize this repeating quality in nature.
People like the great 19th century Japanese artist Katsushika Hokusai.
If you look well enough, you see the shadow of a cloud over Mount Fuji. The cloud is billows upon billows upon billows.
Hokusai with the great wave, you know, on top of the great wave, the smaller waves.
After my book mentioned that Hokusai was fractal, I got inundated with people who say, now we understand Hokusai. Hokusai was drawing fractals.
Everybody thinks that mathematicians are very different from artists. I've come to realize that art is actually really close to mathematics and that they're just using different language. And so for Mandelbrot, it's not about equations. It's about how do we explain this visual phenomenon.
Mandelbrot's fascination with the visual side of math began when he was a student.
It is only in January 44 that suddenly I fell in love with mathematics. And not mathematics in general, with the geometry in its most concrete, sensual form. That part of geometry in which mathematics and the eye meet. The professor was talking about algebra, but I began to see in my mind geometric pictures which fitted this algebra. And once you see these pictures, the answers become obvious. So I discovered something which I had no clue before, that I knew how to transform in my mind instantly the formulas into pictures.
As a young man, Mandelbrot developed a strong sense of self-reliance, shaped in large part by his experience as a Jew living under Nazi occupation in France. For 4 years, he managed to evade the constant threat of arrest and deportation.
There is nothing more hardening in a certain sense than surviving a war, even not as a soldier, but as a hunted civilian. I knew how to act, and I didn't trust people's wisdom very much.
After the war, Mandelbrot got his PhD. He tried teaching at a French university, but he didn't seem to fit in.
They say, well, I'm very gifted but very misled, and I do things the wrong way. I was very much a fish out of water. So I abandoned this job in France and took the gamble to go to IBM.
It was 1958. The giant American corporation was pioneering a technology that would soon revolutionize the way we all live: the computer. IBM was looking for creative thinkers, nonconformists, even rebels. People like Benoit Mandelbrot.
In fact, they had cornered the market for a certain type of oddball. We never had the slightest feeling of being the establishment.
Mandelbrot's colleagues told the young mathematician about a problem of great concern to the company. IBM engineers were transmitting computer data over phone lines, but sometimes the information was not getting through.
They realized that every so often the lines became extremely noisy. Errors occurred in large numbers. It was indeed an extremely messy situation.
Mandelbrot graphed the noise data, and what he saw surprised him. Regardless of the time scale, the graph looked similar. 1 day, 1 hour, 1 second. It didn't matter. It looked about the same.
It turned out to be self-similar with a vengeance.
Mandelbrot was amazed. The strange pattern reminded him of something that had intrigued him as a young man. A mathematical mystery that dated back nearly 100 years. The mystery of the monsters.
The story really begins in the late 19th century. Mathematicians had written down a formal description of what a curve must be, but within that description there were these other things. Things that satisfied the formal definition of what a curve is, but were so weird that you could never draw them, or you couldn't even imagine drawing them. They were just regarded as monsters or things beyond the realm.
They're not lines. They're nothing like lines. They're not circles. They were like really, really weird.
The German mathematician Georg Cantor created the first of the monsters in 1883.
He just took a straight line and he said, I'm going to break this line into thirds, and the middle third I'm going to erase. So you're left with 2 lines at each end, and now I'm going to take those 2 lines, take out the middle third, and we'll do it again. So he does that over and over again.
Most people would think, well, if I've thrown everything away, eventually there's nothing left. Not the case. There's not just 1 point left. There's not just 2 points left. There's infinitely many points left.
As you zoom in on the Cantor set, the pattern stays the same, much like the noise patterns that Mandelbrot had seen at IBM. Another strange shape was put forward by the Swedish mathematician Helge von Koch.
Koch said, well, you start with an equilateral triangle, one of the classical Euclidean geometric figures, and on each side
I take a piece and I substitute 2 pieces that are now longer than the original piece. And for each of those pieces, I substitute 2 pieces that are each longer than the original piece.
Over and over again.
You get the same shape, but now each line has that little triangular bump on it.
And I break it again, and I break it again, and I break it again. And each time I break it, the line gets longer.
Every iteration, every cycle, he's adding on another little triangle.
Imagine iterating that process of adding little bits infinitely many times. What you end up with is something that's infinitely long.
The Koch curve was a paradox. To the eye, the curve appears to be perfectly finite. But mathematically, it is infinite, which means it cannot be measured.
At the time, they called it a pathological curve because it made no sense according to the way people were thinking about measurement and Euclidean geometry and so on.
But the Koch curve turned out to be crucial to a nagging measurement problem: the length of a coastline. In the 1940s, British scientist Lewis Richardson had observed that there can be great variation between different measurements of a coastline.
It depends on how long your yardstick is and how much patience you have. If you measure the coastline of Britain with a 1 mile yardstick, you get so many yardsticks, which gives you so many miles. If you measure with a 1 foot yardstick, it turns out that it's longer. And every time you use a shorter yardstick, you get a longer number.
Because you can always find finer indentations.
Mandelbrot saw that the finer and finer indentations in the Koch curve were precisely what was needed to model coastlines.
He wrote a very famous article in Science magazine called "How Long is the Coastline of Britain?"
A coastline, in geometric terms, said Mandelbrot, is a fractal. And though he knew he couldn't measure its length, he suspected he could measure something else: its roughness. To do that required rethinking one of the basic concepts in math: dimension.
What we would think of as normal geometry, 1 dimension is the straight line, 2 dimensions is, say, the box that has surface area.
And 3 dimensions is a cube. But could something have a dimension somewhere in between, say 2 and 3? Mandelbrot said yes. Fractals do. And the rougher they are, the higher their fractal dimension.
There are all of these technical terms like fractal dimension and self-similarity, but those are the nuts and bolts of the mathematics itself. What that fractal geometry does is give us a way of looking at, in a way that's extremely precise, the world in which we live, in particular the living world.
Mandelbrot's fresh ways of thinking were made possible by his enthusiastic embrace of new technology. Computers made it easy for Mandelbrot to do iteration, the endlessly repeating cycles of calculation that were demanded by the mathematical monsters.
The computer was totally essential. Otherwise, it would have taken a very big, long effort.
Mandelbrot decided to zero in on yet another of the monsters, a problem introduced during World War I by a young French mathematician named Gaston Julia.
Gaston Julia, he was actually looking at what happens when you take a simple equation and you iterate it through a feedback loop. That means you take a number, you plug it into the formula, you get a number out. You take that number back to the beginning and you feed it into the same formula, get another number out. And you keep iterating that over and over again. And the question is, what happens when you iterate it lots of times?
The series of numbers you get is called a set, the Julia set. But working by hand, you could never really know what the complete set looked like.
There were attempts to draw it, doing a bunch of arithmetic by hand and putting a point on graph paper.
You would have to feed it back hundreds, thousands, millions of times. The development of that new kind of mathematics had to wait until fast computers were invented.
At IBM, Mandelbrot did something Julia could never do: use a computer to run the equations millions of times. He then turned the numbers from his Julia sets into points on a graph.
My first step was to just draw mindlessly a large number of Julia sets. Not one picture, hundreds of pictures.
Those images led Mandelbrot to a breakthrough. In 1980, he created an equation of his own, one that combined all of the Julia sets into a single image. When Mandelbrot iterated his equation, he got his own set of numbers. Graphed on a computer, it was a kind of roadmap of all the Julia sets, and quickly became famous as the emblem of fractal geometry. The Mandelbrot set.
They intersect at certain areas, and it's got like a,
And they have little curlicues built into them.
Black beetle-like thing crawling across the floor.
Seahorses, dragons.
Something similar to my hair, actually.
With this mysterious image, Mandelbrot was issuing a bold challenge to long-standing ideas about the limits of mathematics.
The blinders came off, and people could see forms that were always there, but formerly were invisible.
The Mandelbrot set was a great example of what you could do in fractal geometry, just as the archetypical example of classical geometry is the circle.
When you zoom in, you see them coming up again, so you see self-similarity. You see, by zooming in, you zoom, 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 you're zooming in, you're zooming in, and pop. Suddenly it seems like you're exactly where you were before, but you're not. It's just that way down there, it has the same kind of structure as way up here, and the sameness can be grokked.
Mandelbrot's mesmerizing images launched a fad in the world of popular culture.
Suddenly this thing caught like a bushfire. Everybody wanted to have it.
I thought, this is something big going on. This was a cultural event of great proportions.
In the late 1970s, Jane Barnes had just launched a business designing men's clothing.
When I started my business in '76, I was doing fabrics the old-fashioned way, just on graph paper, weaving them on a little hand loom.
But then she discovered fractals and realized that the simple rules that made them could be used to create intricate clothing designs.
I thought, this is amazing. So that very simple concept, I said, oh, I can make designs with that. But in the 80s, I really didn't know how to design a fractal because there wasn't software.
So Barnes got help from two people who knew a lot about math and computers, Bill Jones and Dana Cartwright.
I had Dana and Bill writing my software for me. They said, oh, your work is very mathematical. And I was like, it is? That's my weakest subject in school.
We had a physicist and a mathematician and a textile designer.
We had so much to learn from each other.
I did not know what a warp and a weft is. You know, Jane, her ability with numbers is fairly restricted, if I can put that politely.
All the parameters here, there was a way we were going to communicate. We were going to get together somehow. And it really did happen pretty quickly. The general fashion press thought, Jane's a little nuts. They started calling me the fashion nerd, you know, but that was okay. That was okay with me because I was learning a lot. This was fun and very, very inspirational. I'm getting things that wouldn't be possible by hand. You know, sometimes when I think about things in my head and I say, you know, I just saw light coming through that screen door. And look at the meringue effects that are happening on the ground. Can I go draw that? No way. But I can describe that to my mathematician. This kind of reminds me of... He sends me back the generator, all ready for me to try. And I sit down at the computer and say, well, let's see what it's doing. And I have parameters that I can control. And I keep pushing, and I go, wow, this is not what I expected at all. But it's cool.
Use the force, Luke.
The same kinds of fractal design principles have completely transformed the magic of special effects.
This is a key moment from Star Wars Episode 3, where our two heroes have run out onto the end of this giant mechanical arm. And the lava splashes down onto the arm. My starting point here is to actually take the three-dimensional model and take essentially a jet and just shoot lava up into the air. This looks kind of boring. It's doing roughly the right thing, but the motion has no kind of visual interest to it. Let's look at what happens here when I add the fractal swirl to it. Where this becomes fractal is we take that same swirl pattern, we shrink it down and reapply it. We take that, we shrink it down again, we reapply it. We shrink it down again, we reapply it. And from here on, it's just a case of layering up more and more and more. I've used the same technique to create these additional lava streams. I then do it again here to get some just red-hot embers. Then we take all of those layers and we add them up, and we get the final composite image. My hero lava in the foreground, the extra lava in the background, the embers, sparks, steam, smoke.
Designers and artists the world over have embraced the visual potential of fractals. But when the Mandelbrot set was first published, mathematicians, for the most part, reacted with scorn.
In the Mathematical Intelligencer, which is a gossip sheet for professional mathematicians, there were article after article saying he wasn't a mathematician, he was a bad mathematician, it's not mathematics, fractal geometry is worthless.
The eye had been banished out of science. The eye had been excommunicated.
His colleagues, especially the really good ones, pure mathematicians that he respected, they turned against him.
Because, you get used to the world that you've created and that you live in, and mathematicians had become very used to this world of smooth curves that they could do things with.
They were clinging to the old paradigm, when Mandelbrot and a few people were way out there bringing in the new paradigm. And he used to call me up on the telephone late at night because he was bothered, and we'd talk about it. Mandelbrot was saying, this is a branch of geometry just like Euclid. That offended them. They said, no, this is an artifact of your stupid computing machine.
I know very well that there is this line that fractals are pretty pictures but are pretty useless. Well, it's a pretty jingle, but it's completely ridiculous.
Mandelbrot replied to his critics with his new book, The Fractal Geometry of Nature. It was filled with examples of how his ideas could be useful to science. Mandelbrot argued that with fractals, he could precisely measure natural shapes and make calculations that could be applied to all kinds of formations, from the drainage patterns of rivers to the movements of clouds.
So this domain of growing living systems, which I, along with most other mathematicians, had always regarded as pretty well off limits for mathematics and certainly off limits for geometry, suddenly was center stage. It was Mandelbrot's book that convinced us that this wasn't just artwork. This was new science in the making. This was a completely new way of looking at the world in which we live that allowed us not just to look at it, not just to measure it, but to do mathematics and thereby understand it in a deeper way than we had before.
As someone who's been working with fractals for 20 years, I'm not going to tell you fractals are cool. I'm going to tell you fractals are useful. And that's what's important to me.
In the 1990s, a Boston radio astronomer named Nathan Cohen used fractal mathematics to make a technological breakthrough in electronic communication. Cohen had a hobby. He was a ham radio operator, but his landlord had a rule against rigging antennas on the building.
I was at an astronomy conference in Hungary, and Dr. Mandelbrot was giving a talk about the large-scale structure of the universe and reporting how using fractals was a very good way of understanding that kind of structure, which really wowed the entire group of astronomers. He showed several different fractals that I, in my own mind, looked at and said, oh, wouldn't it be funny if you made an antenna out of that shape? I wonder what it would do.
One of the first designs he tried was inspired by one of the 19th century monsters, the snowflake of Helga von Koch.
I thought back to the lecture and said, well, I've got a piece of wire. What happens if I bend it? After I bent the wire, I hooked it up to the cable and my ham radio, and I was quite surprised to see that it worked the first time out of the box. It worked very well. And I discovered that, much of a surprise to me, that I could actually make the antenna much smaller using the fractal design. So it was, frankly, an interesting way to beat a bad rap with the landlord.
Cohen's experiments soon led him to another discovery. Using a fractal design not only made antennas smaller, but enabled them to receive a much wider range of frequencies.
Using fractals, experimentally, I came up with a very wideband antenna, and then I worked backwards and said, why is it working this way? What is it about nature that requires you to use the fractal to get there? The result of that work was a mathematical theorem that showed if you want to get something that works as an antenna over a very wide range of frequencies, you need to have self-similarity. It has to be fractal in its shape to make it work. Now, that was an exact solution. It wasn't like, oh, here's a way of doing it, and there's a lot of other ways of doing it. It turned out mathematically, we were able to demonstrate that was the only technique you could use to get there.
Cohen made his discovery at a time when cell phone companies were facing a problem. They were offering new features to their customers, like Bluetooth, walkie-talkie, and Wi-Fi, but each of them ran on a separate frequency.
You need to be able to use all those different frequencies and have access to them without 10 stubby antennas.
You can find it in the rainforest, on the frontiers of medical research, in the movies, and it's all over the world of wireless communications. One of nature's biggest design secrets has finally been revealed.
Circles, they were like really, really weird.
So I discovered something which I had no clue before, that I knew how to transform in my mind instantly the formulas into pictures.
As a young man, Mandelbrot developed a strong sense of self-reliance, shaped in large part by his experience as a Jew living under Nazi occupation in France.
Which really wowed the entire group of astronomers. He showed several different fractals that I, in my own mind, looked at and said, oh, wouldn't it be funny if you made an antenna out of that shape? I wonder what it would do.
One of the first designs he tried was inspired by one of the 19th century monsters, the snowflake of Helga von Koch.
I thought back to the lecture and said, well, I've got a piece of wire. What happens if I bend it? After I bent the wire, I hooked it up to the cable and my ham radio, and I was quite surprised to see that it worked the first time out of the box. It worked very well, and I discovered that, much of a surprise to me, that I could actually make the antenna much smaller using the fractal design. So it was, frankly, an interesting way to beat a bad rap with the landlord.
Cohen's experiments soon led him to another discovery. Using a fractal design not only made antennas smaller, but enabled them to receive a much wider range of frequencies.
Using fractals, experimentally, I came up with a very wideband antenna, and then I worked backwards and said, why is it working this way? What is it about nature that requires you to use the fractal to get there? The result of that work was a mathematical theorem that showed if you want to get something that works as an antenna over a very wide range of frequencies, you need to have self-similarity. It has to be fractal in its shape to make it work. Now, that was an exact solution. It wasn't like, oh, here's a way of doing it, and there's a lot of other ways of doing it. It turned out mathematically, we were able to demonstrate that was the only technique you could use to get there.
Cohen made his discovery at a time when cell phone companies were facing a problem. They were offering new features to their customers, like Bluetooth, walkie-talkie, and Wi-Fi, but each of them ran on a separate frequency.
You need to be able to use all those different frequencies and have access to them without 10 stubby antennas sticking out at the same time. The alternative option is you can let your cell phone look like a porcupine, but most people don't want to carry around a porcupine.
Today, fractal antennas are used in tens of millions of cell phones and other wireless communication devices all over the world.
We're going to see over the next 10 to 15 to 20 years that you're going to have to use fractals because it's the only way to get cheaper cost and smaller size for all the complex telecommunication needs we're having.
Once you realize that a shrewd engineer would use fractals in many, many contexts, you better understand why nature, which is shrewder, uses them in its ways.
They're all over in biology. They're solutions that natural selection has come up with over and over and over and over again.
One powerful example, the rhythms of the heart. Something that Boston cardiologist Ari Goldberger has been studying his entire professional life.
The notion of sort of the human body as a machine goes back through the tradition of Newton and the machine-like universe. So somehow we're machines, we're mechanisms. The heartbeat is this timekeeper. Galileo was reported to have used his pulse to time the swinging of a pendular motion, so that all fit in with the idea that the normal heartbeat is like a metronome.
But when Goldberger and his colleagues analyzed data from thousands of people, they found the old theory was wrong.
This is where I show the heartbeat time series of a healthy subject. And as you can see, the heartbeat is not constant over time. It fluctuates, and it fluctuates a lot. For example, in this case, it fluctuates between 60 beats per minute and 120 beats per minute.
The patterns looked familiar to Goldberger, who happened to have read Benoit Mandelbrot's book.
When you actually plotted out the intervals between heartbeats, what you saw was very close to the rough edges of the mountain ranges that were in Mandelbrot's book. You blow them up, expand them, you actually see that there are more of these wrinkles upon wrinkles. The healthy heartbeat, it turned out, had this fractal architecture. People said, this isn't cardiology, we do cardiology if you want to get funded. But it turns out it is cardiology.
Goldberger found that the healthy heartbeat has a distinctive fractal pattern, a signature that one day may help cardiologists spot heart problems sooner.
Please look around the screen for me. All right, Cooper, we're going to do the calibration.
At the University of Oregon, Richard Taylor is using fractals to reveal the secrets of another part of the body, the eye.
What we want to do is see what is that eye doing that allows it to absorb so much visual information. And so that's what led us into the eye trajectories. Under the monitor is a little infrared camera which will actually monitor where the eye is looking, and it actually records that data. And so what we get out is a trajectory of where the eye has been looking.
Oh, it's interesting how they go around the pattern.
And so the computer will get out this graph, and it will look, have all of these various little structure in it. And it's that pattern that we zoom in, we tell the computer to zoom in on and see the fractal dimension.
The test showed that the eye does not always look at things in an orderly or smooth way. If we could understand more about how the eye takes in information, we could do a better job of designing the things that we really need to see.
A traffic light. You're looking at the traffic light, you've got traffic, you've got pedestrians. Your eye is looking all over the place, trying to assess all of this information. People design aircraft cockpits, rows of dials and things like that. If your eye is darting around based on a fractal geometry, though, maybe that's not the best way. Maybe you don't want these things in a simple row. We're trying to work out the natural way that the eye wants to absorb the information. Is it going to be similar to a lot of these other subconscious processes? Body motion. When you're balancing, what are you actually doing there? It's something subconscious and it works, and you're stringing together big sways and small sways and smaller sways. Could those all be connected together to actually be doing a fractal pattern there? More and more physiological processes have been found to be fractal.
Not everyone in science is convinced of fractal geometry's potential for delivering new knowledge. Skeptics argue that it's done little to advance mathematical theory. But in Toronto, biophysicist Peter Burns and his colleagues see fractals as a practical tool, a way to develop mathematical models that might help in diagnosing cancer earlier.
Detecting very small tumors is one of the big challenges in medical imaging.
Burns knew that one early sign of cancer is particularly difficult to see. a network of tiny blood vessels that forms with the tumor. Conventional imaging techniques like ultrasound aren't powerful enough to show them.
We need to be able to see structures which are just a few tenths of a millionth of a meter across. When it comes to a living patient, we don't have the tools to be able to see these tiny blood vessels.
But ultrasound does provide a very good picture of the overall movement of blood. Is there any way, Burns wondered, that images of blood flow could reveal the hidden structure of the blood vessels? To find out, Burns and his colleagues used fractal geometry to make a mathematical model.
If you have a mathematical way of analyzing a structure, you can make a model. What fractals do is they give you some simple rules by which you can create models. And by changing some of the parameters of the model, we can change how the structure looks.
The model showed the flow of blood in the kidney, first through normal blood vessels, and then through vessels feeding a cancerous tumor. Burns discovered that the two kinds of networks had very different fractal dimensions.
Instead of being neatly bifurcating, looking like a nice elm tree, the tumor vasculature is chaotic and tangled and disorganized, looking more like a mistletoe bush.
And the flow of blood through these tangled vessels looked very different than in a normal network. A difference doctors might one day be able to detect with ultrasound.
We've always thought that we have to make medical images sharper and sharper, ever more precise, ever more microscopic in their resolution to find out the information about the structure that's there. What's exciting about this is it's giving us microscopic information without us actually having to look through a microscope. You can see it rises up as the bubbles. We think that this fractal approach may be helpful in distinguishing benign from malignant lesions in a way that hasn't been possible up to now.
It may take years before fractals can help doctors predict cancer, but they are already offering clues to one of biology's more tantalizing mysteries. Why big animals use energy more efficiently than little ones? That's a question that fascinates biologists James Brown and Brian Enquist and physicist Jeffrey West.
There is an extraordinary economy of scale as you increase in size.
An elephant, for example, is 200,000 times heavier than a mouse, but uses only about 10,000 times more energy in the form of calories it consumes.
The bigger you are, you actually need less energy per gram of tissue to stay alive. That is an amazing fact.
And even more amazing is the fact that this relationship between the mass and energy use of any living thing is governed by a strict mathematical formula.
So far as we know, that law is universal, or almost universal, across all of life. So it operates from the tiniest bacteria to whales and sequoia trees.
But even though this law had been discovered back in the 1930s, no one had been able to explain it.
We had this idea that it probably had something to do with how resources are distributed within the bodies of organisms as they varied in size.
We took this big leap and said all of life in some way is sustained by these underlying networks that are transporting oxygen, resources, metabolites that are feeding cells. Circulatory systems and respiratory systems and renal systems and neural systems. It was obvious that fractals were staring us in the face.
If all these biological networks are fractal, it means they obey some simple mathematical rules, which can lead to new insights into how they work.
If you think about it for a minute, it would be incredibly inefficient to have a set of blueprints for every single stage of increasing size. But if you have a fractal code, a code that says when to branch as you get bigger and bigger, then a very simple genetic code can produce what looks like a complicated organism.
Evolution by natural selection has hit upon a design that appears to give the most bang for the buck.
In 1997, West, Brown, and Enquist announced their controversial theory that fractals hold the key to the mysterious relationship between mass and energy use in animals. Now they are putting their theory to a bold new test, an experiment to help determine if the fractal structure of a single tree can predict how an entire rainforest works.
Measurements of its trunk, the next
Enquist has traveled to Costa Rica, to Guanacaste province in the northwestern part of the country. The government has set aside more than 300,000 acres in Guanacaste as a conservation area. This rainforest, like others around the world, plays a vital role in regulating the Earth's climate by removing carbon dioxide from the atmosphere.
If you look at the forest, it basically breathes. And if we understand the total amount of carbon dioxide that's coming into these trees within this forest, we can then better understand how this forest then ultimately regulates the total amount of carbon dioxide in our atmosphere.
With carbon dioxide levels around the world rising, how much CO2 can rainforests like this one absorb? And how important is their role in protecting us from further global warming? Enquist and a team of U.S. scientists think that fractal geometry may help answer these questions.
Baseline. Let's try to get the height of the tree measured here.
They are going to start by doing just about the last thing you'd think a scientist would do here. Cut down a balsa tree. It's dying anyway, and they have the permission of the authorities.
So Christine, as soon as you know the height of that tree, we can actually figure out the approximate angle that we need to take it down on.
Hooking a guideline on a high branch helps ensure the tree will land where they want it to.
Very good, very nice. Jose, perfecto.
Enquist and his colleagues then measure the width and length of the branches to quantify the tree's fractal structure.
8.
10.06.
No, it's 8.
6.3.
6.08.
7 on the nose.
They also measure how much carbon a single leaf contains, which should allow them to figure out what the whole tree can absorb.
So if we know the amount of carbon dioxide that one leaf is able to take in, then hopefully using the fractal branching rule, we can know how much carbon dioxide the entire tree is taking in.
Their next step is to move from the tree to the whole forest.
All right, this is good.
13.2, 3.3 R.
We're going to census this forest. We're going to be measuring the diameter at the base of the trees, ranging all the way from the largest trees down to the smallest trees.
3 meters above the ground.
And in that way, we can then sample the distribution of sizes within the forest.
It's 61.8 centimeters.
Even though the forest may appear random and chaotic, the team believes it actually has a structure. One that, amazingly, is almost identical to the fractal structure of the tree they have just cut down.
The beautiful thing is that the distribution of the sizes of individual trees in the forest appears to exactly match the distribution of the sizes of individual branches within a single tree.
If they're correct, studying a single tree will make it easier to predict how much carbon dioxide an entire forest can absorb. When they finish here, they take their measurements back to base camp, where they'll see if their ideas hold up.
So this is the tree plot, right?
The cool thing is that if you look at the tree, you see the same pattern amongst the branches as we see amongst the trunks of the forest. Very nice.
Just as they'd predicted, the relative number of big and small trees closely matches the relative number of big and small branches.
It's actually phenomenal that it is parallel there. The slope of that line for the tree appears to be the same for the forest as well.
So I guess it was worth cutting up the tree.
It was definitely worth cutting up the tree.
So far, the measurements from the field appear to support the scientists' theory that a single tree can help scientists assess how much this rainforest is helping to slow down global warming.
By analyzing the fractal patterns within the forest, that then enables us to do something that we haven't really been able to do before. Have then a mathematical basis to predict how the forest as a whole takes in carbon dioxide. And ultimately, that's important for understanding what may happen with global climate change.
For generations, scientists believed that the wildness of nature could not be defined by mathematics. But fractal geometry is leading to a whole new understanding, revealing an underlying order governed by simple mathematical rules.
What I thought of in my hikes through forest, that, just a bunch of trees of different sizes, big ones here, small ones there, looking like it's sort of some arbitrary, chaotic mess, actually has an extraordinary structure.
A structure that can be mapped out and measured using fractal geometry.
What's absolutely amazing is that you can translate what you see in the natural world in the language of mathematics. And I can't think of anything more beautiful than that.
Math is our one and only strategy for understanding the complexity of nature. Now, fractal geometry has given us a much larger vocabulary, and with larger vocabulary we can read more of the book of nature.